Good morning. In this section, we are going to revise Unit 5, which is a transistor. The content of this unit are the construction and working principle of a BJT, region of operations of a BJT, and BJT configuration. There are three configurations in a BJT: CB, make it CE, CE, CB, CC configuration. Alpha, beta, gamma are the current amplification factors, and we also draw input output characteristics for each and every configuration, and finally we compared CE, CB and CC configuration. In the second half of unit 5 we learned about FET, field effect transistor, the construction and working of a field effect transistor, and finally we compared BJT and FET. Definition of a transistor is: it is a semiconductor device used to amplify or switching operation of electrical or electronic signals. Generally, transistor consists of three terminals. It will have at least three terminals. Transistors are basically classified into two types. First one is a BJT and the next one is a FET. BJT stands for bipolar junction transistor. BJT is a three-terminal semiconductor device consists of two PN junctions. BJTs also can be used as an amplifier and as a controllable switch in electronic applications. Construction and physical structure of a BJT. We are going to take intrinsic semiconducting material. We are going to divide this intrinsic semiconductor material into three uneven sections. This is a structure for an NPN type of transistor, and this is a structure for the PNP type transistor. And here the doping concentration in emitter is heavily doped, so large number of electrons are present since it is an n-type semiconductor. For a p-type semiconductor, in the base region the doping concentration is very less, so there are only few holes present, and in collector region the collector region is moderately doped, so there are moderate number of electrons present in the collector region. Similarly, with the PNP type transistor, the symbol for an NPN type of transistor is in this way, and the symbol for PNP type of transistor is this one. There are two junctions, emitter based junction or simply J1, and the J2 is a collector based junction. Working principle of a bipolar junction transistor. So to analyze the working principle of a bipolar junction transistor, we are going to consider an NPN transistor. You can also analyze with a PNP transistor, and the analysis results will be the same. In this case, I am going to take NPN transistor. I am going to operate our transistor, which is NPN transistor, in active mode and see how the transistor behaves in an active. The J1 junction, which is an emitter based junction, in forward bias, and J2 junction, which is a collector based junction, in reverse. Here we have a voltage VEB. We applied a voltage, positive voltage across the junction J1. As junction J1 is in forward bias, charge carriers will move from N region to P region and P region to N region. Let's suppose N number of electrons cross the junction J1. As emitter is heavily doped, N will be a large number. N number of electrons cross the junction J1 and enter into the base region. So if you observe in the base region, there are only few holes. So the entered electrons will have less number of holes to pair. So only a 2 to 5% of electrons will pair with the holes. Remaining large number of electrons will remain unpaired. These unpaired electrons will move further due to the large amount of electric field, move further and enter into the collector region. Enter into the collector region, and through the collector region it will go to the positive plate of the battery. So let's suppose the number of electrons entered into the collector region be alpha n. Let n be the number of electrons cross the J1 junction, and alpha n be the number of electrons cross the J2 junction. Remaining electrons, which are n minus alpha n, merged with the holes in the base region. We can also rewrite this one as 1 minus alpha into n. So this is with the voltage VEB. Moving on to the voltage VCB. As VCB is a reverse bias voltage across a junction J2, In reverse bias condition, the current is only due to the minority charge carriers we studied in the PN junction diode. It is also applicable for the BJT. So in a reverse bias, a minority current will be present, which is IC0. It is also called as a saturation current. This current is due to the minority charge carriers. So in conclusion, the collector current constitutes of the current due to these charge carriers and the current due to ICO. It is a combination of two terms. Whereas emitter current, we have only one emitter current, which is due to these charge carriers. Whereas base current is due to these charge carriers. We are going to derive expressions for currents. Hence, the collector current will be equal to alpha times emitter current and a saturation current. Coming to the directions of current, as electrons are flowing in this direction, the conventional current will be opposite to that of a flow of electron. So emitter current will be out of the terminal. So that is the reason why the indication of emitter current will be in this way. Whereas if you see with the base current in the base region, as electrons are moving in this way, the conventional current will be reversed to that of the flow of electron. So base current will be into the base terminal, whereas a collector terminal, it will be in this way. If you apply KCL at the transistor, the current entering the transistor are base current and collector current. The current leaving the transistor are emitter current. KCL is sum of entering currents equal to sum of leaving currents. We have only one leaving current, which is emitter current, and entering currents are IB and IC. These are the expressions for currents in BJT under active region. BJT has three possible configurations. First one is a common base. Base is common for both input and output. Common emitter. Emitter is common for both input and output. Similarly, the collector. First one, common base configuration. We are going to consider an NPN transistor, which is an active mode, and we are going to try to connect these NPN transistor in common base configuration. This is an NPN transistor. Junction 1 should be in forward bias. Junction 2 should be in reverse. And this is the input side of a transistor, and the parameters, which are emitter current and base to emitter voltage, are called input parameters. And the other side of a transistor, the parameters such as collector current and base to collector voltage. This is a base terminal, this is a collector terminal. So base to collector terminal voltage are called as an output parameters. And alpha is approximately equal to ratio of collector current to the emitter current. Collector current is output. So alpha is equal to output parameter by input parameter. Up to 0.7 the current will be 0, and after 0.7 the current will increase exponentially, similar to that of a normal PN junction diode. Next, we are going to slowly increase the output voltage, which is V suffix CB, to 10 volts, and once again draw the input characteristics, which is in this way. If you further increase, you can observe the graph will shift towards y-axis in this direction. This is due to the early effect. In the output characteristics, this is similar to that of a reverse bias characteristics of a PN junction diode. Here somewhere there will be a breakdown voltage. Similarly, we are going to draw output characteristics once again for a different emitter current values. And the second type of configuration is common emitter configuration. Here emitter will be the common for both input and output. As we are operating this NPN transistor in active mode, junction J1 should be in forward bias and junction J2 should be in reverse bias. The final expression, which is a beta, approximately equal to the ratio of collector current to the base current, where collector current is an output current and base current is an input current. So in conclusion, beta is a current amplification factor for a common emitter config. Generally the range of beta will be in 50 to 400. Moving on to the input and output characteristics of a CE configuration. The input characteristics are similar to the VI characteristics of a PN junction diode in forward bias condition, as VCE, which is nothing but output voltage increases, the graph shifts in this direction. Similarly, for the output characteristics, on the x-axis we are going to take VCE, on the y-axis we are going to take IC, and we are going to get a characteristic similar to that of a reverse bias characteristics of PN junction diode. Similarly, with the common collector configuration, here the common terminal will be the collector, which is connected to both input and output side. FET stands for field effect transistor. The field effect transistor is a three-terminal unipolar device that uses electric field to control the current flow. The BJT has three terminals. First one is the emitter, base, collector, whereas a FET will have a source, gate and drain. In the construction section, we are going to see source, gate and moving on. The field effect transistor FETs are classified into two types. The first one is JFET and the second one is IGFET, or also called as a MOSFET. JFET is again classified into N-channel JFET and P-channel JFET. MOSFETs are again classified into DMOS or EMOS. EMOS is again classified into P-channel and N-channel. Similarly, EMOS is classified into P-channel and N-channel. D stands for depletion, E stands for enhancement. Moving on to the construction and physical structure of a JFET. So construction of a JFET is, we are going to take an intrinsic semiconducting material and we are going to dope this intrinsic semiconducting material with N-type impurity, assuming we are making N-channel JFET. I am going to dope this intrinsic material with the N-type impurities except for this region. In this region, I am going to dope with the P-type impurities. On the one half of N-type impurities, I am going to connect one terminal and call this terminal as a source, and the other half of N-type impurities, I am going to connect one more terminal and call this one as a drain, terminal D. And we have two more terminals, this one called as a gate terminal and this one is also called as a gate terminal. So internally in a JFET there are four terminals, but externally we have only three terminals. Internally they are going to connect these two gate terminals and we are going to get only one gate terminal at the output. So in conclusion, there are three terminals. This one is a drain terminal, gate terminal and a source terminal. Similarly, for a P-channel JFET, P-type impurities, this section will be the N-type impurities and this one also N-type impurities. The passway from source to drain is called as a channel. Here the passway is made up of N-type impurities. This one is called as a N-channel. The passway is made up of a P-type impurities. So this will called as P-channel. Moving on to the working principle of a JFET. For analysis, we are going to consider an N-channel JFET. The analysis will be similar for the P-channel JFET, whereas in P-channel JFET, the charge carriers will be holes, whereas here in N-channel JFET, the charge carriers are electrons. As the name says itself that the channel is made up of N-type material. In N-type material, electrons are the charge carriers. So the current is due to the electrons. Coming to the circuit diagram, here gate terminal and source terminal are short circuited and a voltage source of VDD is applied between source and drain terminal as shown in the figure. So if the voltage source is a 0, the depletion region will be the yellow one. This one will be the depletion region. It is evenly distributed on all sides. The thickness of depletion region is same on the all sides. If we slowly increase the voltage VDD and observe the shape of the depletion region changes. So let's say a voltage of 4 volts is applied across source and drain terminals. As source is taken as a reference, this will be a 0 volts. The gate terminal and source terminal are circuited. So gate terminal will be also 0 volts. This one will be also a 0 volts. As the potential of a battery is 4 volts, the drain terminal voltage will be 4 volts. Voltage at this particular point is 4 volts and voltage at this particular point is 0 volts. So halfway between the drain and source terminal at the center, the voltage will be half that of potential difference, which will be a 2 volts. And if you measure the voltage over here at the 1/4 of the length, it will be 1 volt. And if you measure at this particular point, it will be 3 volts. The electric field intensity slowly increases as we move from source to drain. So if you observe at this particular point, which is a 1 volt point, the N type is connected to higher voltage level and a P side is connected to 0 volts, which means a lower voltage level. So we can say that this junction, PN junction, is in a reverse bias condition. In reverse bias condition, as voltage increases, the width of the depletion region increases. So for 1 volt, let's assume the width of the depletion region will be at T1. Moving on to the next point, at this particular point, N side is connected to a 2 volts and the P side is connected to a 0 volts. Now the potential difference is a 2 volts. For 2 volts, the thickness of depletion region will be T2. As we know, for a PN junction diode in reverse bias condition, as reverse bias voltage increases, the width of the depletion region increases. If you observe, here the reverse bias voltage is 1 volt and here it is a 2 volts. Hence, the thickness of depletion region over here is more when compared to the thickness of the depletion region at this particular point. So moving on to the 3 volts, here potential difference is further more. Hence, if T3 is the thickness of the depletion region, then it will be greater than T2 and T1. Hence here the thickness of the depletion region is further increased. So overall we will get a depletion region in this shape, an uneven depletion region where the thickness of depletion region slowly increases from bottom to top. Similarly on the other side also. Our next concept is comparison between BJT and JFET. The symbolic representation for a BJT of NPN type is in this way. The arrows is towards the emitter terminal, whereas in NPN type BJT, the arrow is away from the emitter terminal. Coming to the JFET, for an N-channel JFET, the arrow is away from the gate terminal, whereas for a P-channel JFET, the arrow is towards the gate terminal. Here the three terminals in BJT are base emitter collector, whereas in a JFET are gate, drain and source. Moving on to the next point, BJT is a bipolar device. So the current in a BJT is due to both charge carriers, hence it is called as a bipolar device, whereas in FET, field effect transistor, gate doesn't have any involvement in the drain current. The current only flows through the channel, which is either N type or a P type. So the current is only due to the single type of charge carrier. So FET is called as a unipolar device. Moving on to the next point, we are going to discuss the third point after fourth point. In a common emitter configuration, the collector current is approximately equal to beta times IB, where beta is the current amplification factor in common emitter configuration. Where if you observe, the output current, which is a collector current, is a function of base current, which is an input current. As we vary the input current, the output current varies. So we can say the BJT is a current control device. It depends upon the input current. Whereas coming to the field effect transistor FET, the expression for output current, which is drain current, is this one. So if you observe, both these terms are a constant, The only variable is VGS. So ID is equal to drain current. The output current is a function of VGS. Make a correction over here. It is VGS. So we can say field effect transistor is a voltage control device. It depends on the voltage, which is VGS. Moving on to the next point, the output current is approximately equal to the emitter current, whereas the output current in a field effect transistor is equal to the source current. The BJT has a high power consumption, whereas FET has a low power consumption. High power consumption results to bad thermal stability. So BJT has a bad thermal stability, whereas a FET has good thermal stability. BJT has a higher noise level and a FET has a lower noise level. And the size of a BJT are larger when compared to the size of JFET. And the last point is we cannot interchange the terminals in a BJT. If a terminal is meant to be used as an emitter, it should be used as a emitter. It cannot serve as a base or either as a collector. Whereas in a field effect transistor, we can change the terminals of a drain and source. If we interchange the terminals of drain and source, the performance will be the same. There is no degradation in the performance of JFET. So in conclusion, first read the physical construction of a BJT and different BJT configurations which are CE, CB, CC and comparison of three configurations. Next, learn working principle of FET and comparison of BJT and FET. Finally, learn the working principle of a BJT and then construction and physical structure of FET.